Okay, so chapter 3 that we did yesterday was all about categorical data plots. So when we're talking about bar charts, pie charts, bivariate tables, or the contingency tables, when we're talking about, what are some of the other ones? Segmented bar charts. So all of those things, we're dealing with categorical data. Chapter 4 is all about how we display quantitative data. And the biggest one out of that is going to be our histogram. But dot plots are also really important. And of course, box plot. Well, okay, fine. So I basically circled everything except the stem and leaf plot. You will need to know about it, but we really don't use it as much. So let's jump into it. So I start with the stem and leaf plot. So you can see what's going on. We do have quantitative data going on, and it's being displayed here. But the one thing, and it says up here, this is good information because it preserves the data. And we're going to talk about the stem and leaf in a second. But you could probably imagine, just seeing how this is created, that if you had 1,000 data points, this would be a mess. You would not want to be looking at a stem and leaf plot with 1,000 data points. This is, what, guessing 25, 30 points right here. So this is not too bad. So it kind of limits how useful it is. So the way that this works, and you would almost always have a key. So it's not showing up here, but you'd have some kind of a key that says, in this case, 8 is like 88. So maybe this right here represents your tens place. And then all of these leaves represent your ones value. So every leaf represents a different data point. And that's why you have 2 ones right here. Well, this represents 41 showed up once in the data set, and it showed up a second time. So we're going to have 41, 41, 43, 47, and 48 as data points. Now, it's important to read the key for something like this because it's not always tens and ones. Like this 2 could easily represent millions. So, or sorry, this column here could represent millions, and this is your 100,000s. So maybe instead of 41, we're talking about 4.1 million. Now, that's kind of unusual, but it can happen. So just make sure you find the key, and really you're going to be looking at this for interpretation. I guess it's possible they could ask you to create one, and certainly in your homework you'll probably need to create one, but there you go. Quantitative data, it is useful because you can still, well, let me go back to it just to say that point. This is good because if this is all they gave you, you could still look at it and you could say, oh, well, 64 is one of my data points because you can see the 6 and the 4. As opposed to some other displays. The dot plot is quite useful because it's really good for collecting data. Imagine I wanted you guys, and we will create dot plots. It's going to work a little weird. Well, no, it'll work fine for us because even with a small group. But if I wanted to collect data and I said, okay, you guys are going to do this activity and report your results, and your typical results might be 3, 4, 5, 6, or 7, then you can just be like, okay, well, I got a 5, and then I got a 4, and then I got a 6, and I got another 5 and another 6, So it's really easy to collect data that way. Though again, once you get up to a lot of data points, it becomes really, really unwieldy to use something like this. So this is kind of the cousin of our next one, which is the histogram. So the difference between these two, between the dot plot and histogram, are almost equally useful as far as how much we use them in this class. Well, that's not quite true. We use the histogram a heck of a lot. So the histogram, we lose individual data points. So when we go back to the dot plot real quick, I can tell you that there were 1, 2, 3, 4, 5, 6, 7 data points that had a value of 2. All right, and we know how many. But when I go to this one, I could kind of tell you how many had a value of, in this bin, but it works a little differently. First of all, it's not as easy to tell. And secondly, these values are not all the same. So we're talking about what we call discrete values with the dot plot. But we're talking about, and we say discrete, maybe the actual value is 3 and I got that 6 times. But here, my value was between 1 and 1.5, and I got it about 24 times. 24. So anyways, kind of just general information there. So when you have large data sets, this is the standard. That and the box plots, which we'll see next. Quantitative data are separated into equal width bins. And so that's what these are referred to. So the bin right here is going from 3 to 3.5. That's the bin length. And notice that every one of these has a width of 0.5. So once we determine our bin width, we keep it constant. The y-axis can show relative frequency instead of counts. And over on the right, you can see relative frequency being shown. It doesn't change the shape of your histogram, but it does change how we kind of look and interpret it. Now you can say, instead of the raw number, we can say it has been from like 4.5 to 4. No, that's 5 to 5.5. It has almost 25% of the data. Okay. This is a small nuance, but it's worth knowing. The bin typically includes the lower value, but does not include the upper one. So this bin right here would go from 4 to less than 4.5. Okay. And any value that falls right on the line, which is not, depending on the data set, it's not sometimes very common. But if it does fall right on the data value, you would put it in the one on the right. So a 4 would go into that bin, not the one on the left. Again, most of the time, we're going to be looking at histograms that are already created. So that's something to know, but probably won't be a major deal. And this is actually a question that came up yesterday in class. So we're going to kind of go in more detail today. When you're creating a histogram, you do kind of have the option as to how wide you want to make your bins. And if you make them too big, you don't get much shape, and there's not a lot of resolution to it, if you will. So it's not going to give us a lot of information. But if you make it too narrow, then notice you get these discrete values. And notice right here, we have a frequency of 10 for that. But here, the highest frequency we ever get is 3, because these are very narrow bins. So you want to kind of shoot for a happy medium. And depending on the number of data points you have, that can vary. But you want usually at least 10. But again, if you don't have very many data points, so I don't want to give you that as an actual rule you need to follow. So let me summarize all this by saying you won't frequently need to create these charts. So be aware of how to do it without dwelling too much on feeling like you need to create 100 of these to get mastery. Okay, so these two, the histograms versus bar charts, do have some important distinctions between them. First of all, well, I think it's the first one. Well, it might show up on this list, but histograms are for quantitative data. Bar charts are for categorical data. And histograms have a natural order to them. And what I mean there is that we're always going to be counting up. Typically, we're going to, well, it's quantitative, so we're going to have some kind of a scale down at the bottom with a number line, basically. So we're going to start at the lowest number and work our way up to the biggest. So if I had a value that was, let's just say 6.2, I couldn't just put the 6.2 bin wherever I wanted. It would need to go in here because that's where it falls in the number line. The bar chart, on the other hand, there's no natural order. Now you can see right here that they have white, then Hispanic, then Black, then Asian, then multiracial, Native, other, Islander. So they put it in this order because it goes from the biggest representation to the smallest. But if Hispanic overtook, they'd probably just flip white and Hispanic. It's not a big deal. But here you can't just flip it when one of these values gets bigger. So that's kind of important to keep in mind. Bars and bar charts can be placed in any order. Okay, I just talked about that. Bars are connected in histograms. So this is kind of a representation thing, the way that we show it. In bar charts, we do keep the bars separate. So if you ever see them connected, that's not good chart design. And of course, the last thing is the very first thing I said. Histograms are for quantitative and bar charts are for categorical. Okay. So this right here, this is a random slide in some respects, but it is a helpful acronym to remind you how to describe a histogram. We're going to learn a few acronyms during the course of this class, and it's going to be hard to keep them all straight. Keep in mind that these presentations are in the Canvas classroom, so you don't need to copy down notes from this unless it's something especially important for you that you don't want to forget, like you want to put an extra asterisk next to it. But DISCO refers to distribution, spread, center, and outliers / odd features. So just as a heads up at the beginning, what you might see is, here's a distribution. I want you to describe the distribution. And you're going to need to go through and make sure you've talked about all 4 of these things. So you might, and we'll talk about how to do that with each part, but you want to kind of hit all 4 aspects. So if we look into distribution a little closer, the distributions can be described in lots of different ways. So here we go. Is it unimodal, bimodal, multimodal, or uniform? Okay, so unimodal, you know the word mode. Mode is the most frequent result in a data set. So a mode is going to be represented in grams by where there's the hump, where there's the peak. So this is unimodal because there's only one spot. So I'll just draw an arrow to connect those. There's only one center, or well, I don't want to say center, but there's only one place where the data kind of clumps together. This one is a perfect example of bimodal because you can see there's a lot there and then it drops off and then there's another one. So when we talk about modes here, you're looking for humps in the data. Multimodal is very unusual. I don't know that it ever shows up, but if you have more than 2, that would be called multimodal. And then uniform is when there's really no spot where it peaks and it seems to be pretty constant. So these are all great ways of describing your distribution. Now, you can get a little more nuanced than that too, because you could have it skewed or symmetric. So here we have what's called a negative skew, because if you were to kind of model that with a smooth curve, you do have a mode. It is unimodal. I think we can agree with that. It's unimodal, but it definitely has all these values that are kind of lower. So when you have it, and let's compare it to this one up in the corner, this one seems to be symmetric. If I drew a line right here, I could almost reflect those bars onto it themselves. So this one, you know, obviously you can't reflect it onto itself, and it does have a skew. You could refer to this 2 different ways. You could call this, and I'm talking about this one again, you could refer to that as a skewed left or a negative skew. So negative because it's skewed in the negative direction. Now the other one skewed to the right is an example here. It's worth pointing out before we talk about the skew that this little gap in the data, or where it drops down a little bit, that does not make it bimodal. So I would still call this unimodal. You can see the difference between the bimodal when you look at the one above. So this is still something I would call unimodal. But when I kind of smooth this out, I get these outliers to the right. And they're not necessarily outliers, but we do have data that stretches over to the right. So I would say this has a positive skew because it's being skewed in the positive direction, or you could just say skewed right. There's no preferred way of doing it. So if you like one way of saying it versus the other, skewed left makes sense because you just see what direction is the tail going. We refer to these as tails. So the tail is going to the left, so it's skewed left. That might be easy for you guys to remember. Okay, and I'll pause right there because I'm talking quite a bit, and I just want to make sure if there are any questions you can ask them. Okay. So the next is the spread of the data. Sorry about that. And there's two main ways that we can talk about the spread. And one of them, so since we already talked about the distribution overall, the shape of it, if the distribution is symmetric and unimodal, so I will, and actually both of these are examples of symmetric and unimodal, but if it's symmetric and unimodal, then we can use the standard deviation. And technically, if it's uniform also, that works, but really symmetric and unimodal. Symmetric, of course, meaning that it's not skewed left or right, and unimodal, it only has one mode. So if the distribution is not symmetric or not unimodal, then we need to use the IQR, the interquartile range, and we're going to go into more detail with that in a little bit. So another measure for spread is range. If you have no other information available, then you can talk about the range, which is just, do I have a slide on that? There it is. It's just your biggest value minus your minimum value. So let's say they don't give us any information on this, and we can learn to read this chart later to kind of estimate the standard deviation of it. But for right now, let's say that we're not comfortable with that. We can go from the biggest value to the smallest value. And this is going to go from around 65, because this bin right here centers at 65. And this bin right here goes down to 40. Okay, now, because we're dealing with bins, we don't know the exact values. So I can't say the range is 25, but I could say the range is approximately 25, plus or minus. Okay, so just to wrap that part up, if there is no other information, the range is an acceptable thing to talk about. But when we get further into it, we will find better ways of talking about the spread. Okay, the center. We have two measures of center. If the distribution is symmetric and unimodal, use the mean. If the distribution is not symmetric or not unimodal, use the median. Okay, the mean is the average. We have some terminology. It's worth bringing up now. We're going to use this frequently. X bar. Anytime we put a bar over anything, we're talking about the average. So if I wanted to get the average height in this class, I could refer to my final number as height bar. And then whatever that number is. So just keep in mind the bar represents that. The median is the middle value. If it's an even number of data points, you use the average of the two middle values. These are concepts you should already be familiar with, so I'm not spending much time with this. You can use your calculator to find these, and we will, in fact, we can look at that more. And make sure to give the units when you're giving the center. So if you have a data set and there's a histogram that's given, so I'm just going to model it. Let's say that you have this unimodal symmetric data set, and it tells you the mean is 25. Then what you can do is you can say 25 what? If this is like, I don't know, what would 25 be an average of? 25 years of someone on a football team, professional football team. That would be a young team, I guess, but we're going to go with it. You'd want to report that in years, 25 years. All right. And here we go. The mode is technically another measure of center, but we don't use it typically. In fact, if we don't have any information except for a you know, a histogram, I probably wouldn't even talk about the mode there. I would say the mean is, or the median is going to be approximately somewhere in this range, right? So whatever these values are right here, I would say, oh, the mean or the median is approximately there. And we're going to talk about which one's most appropriate. Well, we already did that. So let me actually quiz you guys. If you read this again, and I get rid of this, in this distribution, would it make more sense to talk about the median of the data or the mean of the data?
The median.
The median, perfect. So this is not symmetric, this data set. So in this case, our best measure of center is going to be the median. All right. So, oh, well, here we go. I forgot I had this slide. What should we use here?
Median.
Median. So now this is, let me see, do I have anything else? So the median, first of all, the mode is right here. So we can just start with that in this case. I'll just write it down, the mode. The median is, where do you think the median would be for this data set? And you can draw a line if anyone wants to draw on the screen.
Would it be around like 6?
It wouldn't be that far over. So we obviously have a big clump of higher values up here, and that's going to affect this, but one of these is affected more than the other. So let me actually do it this way. I'm going to put one line right here and one line about right here. Which of these is the median and which of these is the mode? Sorry, median and mean. For mean, you can just write X bar.
The one farther right would be the median.
Actually, it's the other way around.
Oh.
No, and that's okay. That's okay. The mean is more affected by outlier values than the median is. And that's because of how we calculate it. Keep in mind, for the median, we would take and list all these values. I don't want to write all these down, but let's say this is like 1.8 and then 2.1, 2.2, and whatever the case. We have all these values here, and I just put them in order all the way up to up here, which is, what is this, 10.6. So dot, 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 down to 10.6. If I added another value down here, let's say that there is one other value in this, and there might actually be one. So let's say this is, that should be 11.6, I'm sorry. No, that should be 11.3. Okay. Here I go trying to wing it and I'm messing up. So let's say I added one more value up above, 11.6. All that does is it moves my median down one number. So if I have a bunch of data points and I've got a number of them here at like 3.8, 3.8, 3.9, then it's just going to move this down one number. And so my median might not really be affected that much. Is that making sense? Okay, so if there are any questions, please feel free to ask. But mean, what we do is we take all these data points. So I'll just put x sub 1 plus x sub 2. And this x can mean just any one of the data points. So there's the first data point, the second, the third, plus dot, 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 up to the last one, x sub n. And I divide by n, which is the number of data points. Now, if I added a really huge value right here, let's say I added one that was like plus 16, like this is way off the chart, a major outlier. That is going to have a major impact because it gets folded into the calculation. So if we can see the difference of how mean and median are created, then we can see why the mean is actually affected more by outliers. Okay, any questions there? Okay, so that is the reason why, just got rid of everything. When we have a skewed distribution like this, we want to use the median because a median is more resistant to outliers. And we only use the mean when we have a nice uniform, symmetric distribution, not uniform, unimodal, symmetric distribution. There's no real outliers here that are going to screw this up. And it's the preferred measure if we can swing it. Okay, so that's dealing with the center. And there we go, that kind of summarizes it. The median is only slightly pulled in the direction of the skew, so it is resistant. Okay, median is the preferred measure of center when the data is skewed. So that just wraps up what I said. Then we have the outliers or odd features. So in this one right here, we got this nice uniform symmetric histogram, except we have this gap of data, and then we have this outlier here. And here, I wouldn't call this an outlier, but there is a gap in the data. So we can refer to anything unusual in the histogram, and we can just say, oh, there's a gap in the data from 9 point whatever to 9 point whatever, and there's an outlier at this point. So I have a gap, and I have an outlier. And then if you thought it was unusual, then you could point out right here that there's a gap in the data. Now this, like I said, is not probably an outlier. It's not super far away, but we just happen to have a gap from 80 to 90. All right, and we will put numbers on outliers later. But that's the basic idea. All right, and so that is it. So let me actually, before we look at this, I'm going to jump back to this one. So the distribution, is it uniform? Is it bimodal, unimodal? Is it skewed or symmetric? Is this, what's the spread like? You can talk about the standard deviation or the IQR, which we're about to jump into, or you can talk about the range. The center, mean or median, where does that fall? And if you don't know exactly, approximately where does it fall? And finally, the outliers. So that's what you need to describe. Okay, and this is, I think this is the last little bit of the important stuff here. Yeah. So let's jump and look at this, box plots. So the box plots, this is the other major one. And what you lose with a box plot is the shape of the distribution. But it does give you a really, really quick way of kind of getting a feel for where the data lives. And we'll talk about how this is created. And if you had a lot of box plots, you could compare these, and that's a great thing to really quickly assess. So if I gave you a bunch of histograms, you could do some kind of an assessment on that. You know, maybe I gave you those 3, but it's going to be a little bit more difficult to draw a quick comparison between those compared to if I gave you a bunch of box plots. So maybe I gave you this box plot, I give you this one. Oops. All right. So if I gave you those 2 to compare, you could quickly kind of see the differences between them. Now we haven't talked about the numbers on here yet. So what we have are 5 numbers. This is why we call it the 5-number summary. It's going to be important to know that what the 5 numbers are. We have the min. So this right here, maybe I'll point it out on this one. This is the minimum value. Now, technically that's not correct. We do have this value down here. That's the minimum value. But let's ignore outliers for now. I'm going to pretend like that's not on the chart and this isn't on the chart. We're going to talk about that more tomorrow. So let's say it's just this. So you have your minimum value. You have Q1, which is called the first quartile. Then you have in the middle of the median, and then Q3, which is the third quartile, and then you have your max value. So what's special about this? Well, and if you read, or if you remember from years past, you hopefully remember 25% of the data lives in that quartile. 25% lives between Q1 and the median. 25%, you can see the pattern here, goes from the median up to the third quartile, and 25% of the data lives between Q3 and the max. So this splits it up into the 4 quartiles, and it really is good. The interquartile range, you can see marked right here. This shows the actual range between the first quartile and the third quartile. And you can see right there, it shows up. So this is the range. Well, okay, so let me start over. The range represents this entire distance. But that doesn't help us a whole lot, because you can have a crazy value that lives, well, like right here. If I still had this value and this value, then my range is huge. But the interquartile range stays relatively small. All right. So if we can just look at the middle 50% of the data, and remember, we got the 25% just above the median and the 25% just below the median. And so what we're saying is we don't care about the most extreme big values and the most extreme small values. Where does the middle 50% of the data live? And that's what we call the interquartile range. All right, any questions on this so far? Okay. So these values, we can find them. In fact, tomorrow we're going to be finding them using the calculator. And today we're going to be doing it the old-fashioned way, using our brains. Okay. So before we can find a 5-number summary, we want to put this data in order, because the median is determined by having all your data put in order. So let's see, how do we want to do this? You guys can just work independently for a minute. I'll kind of write my numbers up on screen, but you might want to copy this data set down onto some scratch paper, and we'll work through getting the 5-number summary. Okay, so what is our min for this?
1.
All right, and the max is?
98.
98. Those are always the kind of the low-hanging fruit for your 5-number summary. It's pretty easy to find those. Okay, so the median, what number did you guys get?
$31.5.
31.5. And how do we get 31.5?
Because the 30 and the 33 were both left in the middle, so I just took the average of those.
Perfect. We add those up, we get 63 divided by 2. There it is, 31.5. Okay. And of course, if you had to do this, you could just do all this stuff in your head. Not a big deal. Now, here's the thing. With Q1 and Q3, I now know that my median is right here. It's actually not in my data set, but my median is 31.5. So I'm going to go ahead and draw a line right there. And what's left over is I've got this data above the median, this data below the median. 50% of the data is above, 50% below. Now I can just look at those 9 data points on, let's start at the one on the lower side. We can look at Q1. So what is the median of the lower half?
Is it 17?
It's 17. We're looking at 9 data points, and 17 happens to be right in the middle of those 9. So that's it. And we do the same thing for the top, and what does that happen to be?
54.
54. Okay. Just making sure I did my math right. 54. So we are essentially now we're gonna figure out our IQR. Now I'll pause there. If there are any questions, you can ask any of them here. Okay. So the IQR is not part of the 5-number summary, but that's okay because the IQR is pretty straightforward. We saw the formula a minute ago. And remember, this stands for interquartile range. So it's basically Q3 minus Q1. So in this case, it's going to be 54 minus 17, which is 37. And that's it. So to explain what the IQR is, it's not a data point. The Q1 is a data point. This is telling you the threshold, the cutoff point for where your first 25% of the data ends. And so that is a data point. 37 is not a data point. It's saying that there is a range of 37 between your first quartile data point and your third quartile data point. So if all of these values were shifted up, if I added plus 10 to everything, then the numbers in my 5-number summary would all change by plus 10. But the IQR would not. The range of the between Q1 and Q3 stays constant. Okay. So the range also takes the same unit. So I don't know what this is, but let's say this is pounds for some reason. So we're dealing with pounds. So my IQR would be 37 pounds. Okay. Any questions on this? Okay. Standard deviation. This one is not something we're going to go into in class because you can see the formulas right there. This is the formula for standard deviation. This is the formula for what we call variance, which will matter in this class. But for right now, just know that your variance is the exact same thing, just not square root. So I am not going to go through, we are never ever going to calculate standard deviation by hand. You can see it's a pain in the butt to do, but your book does give a very good explanation of it. And I want you to read that and make sure you understand it. Just keep in mind that your standard deviation is, in essence, the average distance any data point is from the center, from the mean. So if I do have a uniform, or a unimodal, I keep saying uniform, a unimodal symmetric data set, each data point that makes this up, and there's a lot of data points. So let's say I had one right here that was part of this bin. This data point is going to be on average, this standard deviation away. Some of them are really close, some of them are right on the line, some of them are far away, but on average, they're going to be that distance. So that's just one way to think about it. Again, this only works when you have a unimodal symmetric distribution. Otherwise, you're going to be using IQR. So luckily, our calculator will always do this for us. And just a couple of other plots to show you before we, dang, we're going to finish up pretty early. You know why that's the case? Because first of all, I just planned it out that way and I'm amazing. But secondly, is because when I gave this presentation last year, it was a Wednesday presentation. So it's going to be shorter anyway. Okay, so this is a weird chart that you've probably, well, you might have seen one before, but it's not a usual one. And it's pronounced ogive. So this is an ogive. And I will pretty much tell you that you're only ever going to be interpreting something from an ogive. They're also called cumulative frequency graphs. And they are useful for answering certain types of questions. So essentially what's happening is we're turning a histogram that looks like this into an ogive that looks like that, because we're saying the cumulative frequency. So notice that the first half of this looks like a regular, distribution like I just showed you. But then it keeps going up because we are cumulatively adding to the total. And we eventually get up to the top where we have 100% of the data. So this builds up to 100% of the data. So the kinds of questions that these are useful for is to say, what data point falls at the 80th percentile? And the 80th percentile, we'll definitely talk about, oh no. We'll talk about this more. Sorry, I have to take care of something real quick. So when we talk about 80th percentile or any percentile, and we're going to talk about this more, but that is, and maybe it's worth it to kind of talk about it now. 80% of the data falls below a specific value. So when you guys took a pre-ACT or PSAT, if you did that, it probably gave you some of your scores as far as your percentile rank. Like, oh, you were in the 94th percentile, which means 94% of people scored lower than you. And anyways, if I ask for the 80th percentile, this is really great because I can find what percentile on this y-axis right here. So I said 80th, so I'm just going to come over to here, and then I can come down, and it looks like my data point is going to be about, I don't know, I'm just going to guess, 0.6. Okay, so in this particular data set, 0.6 would represent the 80th percentile. So it's a nice visual way of doing that. We will have other ways of answering questions like that. So it's not likely that this is going to be a major thing that you're going to see on your test. Okay. And maybe it's worth it to do a brief diversion from this for a second to talk about the AP test, because there are a lot of like minor pieces of content in this class. And, you know, it's easy to forget, like, oh, I forgot that one small concept. Like, if you're worried like, oh, it's going to be a collection of all these little small pieces of information that I've forgotten, that's really not what most of the AP test is. It's going to be kind of reinforcing concepts that are very central to the idea of this class. So when you do have something that's kind of obscure like this, you might get it right, you might get it wrong, and you can kind of interpret it based on your statistical intuition without having to memorize stuff. But here's my whole point. To get a 5 on an AP test, and it changes every year, but typically you need to get about 70% right. And to just get a 3 on the test, again, this changes, you need to get about 50%. So you can't quote me on these numbers, but the whole point is if you're like already trying to talk yourself out of doing the AP test, I do want to point out right now that you don't need to know 100% of the information in order to do really well on the test. You need to have a good foundation. Okay, so one last thing to say about the AP test, and this is something I learned recently. The amount of content that we cover in this class is actually more than you would cover in your, first semester statistics class in college. Because there's not as much time in college. So we actually cover a lot more information, which is why, getting a 70% on all the content that we cover, that means that you would have mastered 100% of the content at college. So you're getting more education than you would by taking this in college. So there you go. All right, it's enough about the AP test. Let's just wrap this up for the day. The last one to talk about here is a time plot. This is mentioned in there. It's actually a form of a scatter plot, which we're not going to get into until 2 units from now. But a scatter plot is basically just, a time plot is just using time as one of your axes in a scatter plot. And this is good for seeing change in temperature through time. That's just one example, but a change in anything through time. So there we go. Time plots, again, these are just going to be for interpretation sake. And with that covers in kind of very short detail everything that's in chapter 4. So I want you to this is already posted on the website. For the first unit, I am not having you turn in your homework. So it'll be starting in unit 2 that you'll actually have to turn in your work. So until then, it's all on you to hold yourself accountable. And remember, after that, you only have to do one problem to turn it in. So it's still on you to make sure you're doing all your homework. All right, I feel like I've talked enough. If you have any questions, please stick around. But if you are feeling good with everything, have a wonderful weekend, and I will see you on Monday.